Hello, we will learn neural network today. We will learn it with TensorFlow Playground. So TensorFlow Playground. So neural network playground, TensorFlow. So yeah, we have some interesting one. Epoch, learning lane. Well, there are many interesting concepts. So well, let's read the explanation first. So what is neural network? Neural network is a technique for building a computer program that learns from data. It is based very loosely on how we think the human brain works. First, a collection of software neurons are created and connected together, and allowing them to send messages to each other. So it means that we have neurons, and then they are connected to each other. So it is like a sequential neuron. So information flow this way. And then next, the network is asked to solve a problem, which it attempts to do over and over each time, strengthening connection. So we keep feeding the data and then iterating the model, basically uh, iterate its estimation process. So well, the relevant relationship becomes more and more stronger. Okay. And then each time strengthening the connections that lead to success and diminishing those that lead to failure. For a more detailed introduction to neural network, you visit here. Okay. For more technical overview, you can try this. Okay. So it is cool. So what is it? And then, yeah. So this is cool. Can I repurpose it? Of course, please do. We've open sourced it on GitHub with hope that it can make neural network a little more accessible, easier to learn. So yes, you can check it. We've also provided some control below to enable you tailor the playground to a specific topic or lesson. Okay. Well, now we have every buttons. Okay. So what do all the color means? Orange and blue are used throughout the visualizer in slightly different way, but in general, orange shows a negative values while blue shows a positive value. So here, well, this is data. So orange is the negative value, blue is positive value. So we are gonna build a neural network model that predict blue and yellow given the data. Okay. So the data points are initially colored orange or blue, which correspond to positive one and negative one. Okay. In the hidden layers, so here, okay, so they are features. We have input variable, and then we have hidden layers, and we have output. So we have hidden layers. Here we have two hidden layers. Hidden layers. Two hidden layers. So hidden layer one, basically two hidden layers. So basically hidden layer one and hidden layers two. So this hidden layer has four neurons, and this hidden layer has two neurons. Yeah, this is good. This is good. And then, so in the hidden layer, the lines are colored by the weights of the connection between the neurons. So blue shows a positive weight, which means the network is using that output of the neuron as given. An orange line shows the line is assigning a negative weight. So here we have blue and yellow lines. So blue, this is positive, weight is 0.46 positive. Here yellow, weight is 0.33 negative, something like that. Good. And then, yeah, an orange line shows that network is assigning negative weight. In the output layer, the dots are colored orange or blue depending on their original value. So in the output, we have dots. Some are blue, some are red, and their original values. The background color shows what the network is predicting for a particular area. So here, the prediction is not so good, so there is no prediction over here in this state. So the intensity of the color shows how confident the prediction is. Okay, so let's try it. So let's try to remove all hidden layers. Okay, 0 hidden layers here. And then let's remove all the data. Okay, and then let's pick the very simple one. Okay, actually pick this one. So we wanna build a model that distinguish blue and yellow, blue and orange one. So let's use one data. Okay, so x1. So x1 is the axis. Yeah, so x1 is the value in the line of this one. So because we are choosing only x1, so basically it split the plane this way. So it is reasonable split. So if we run this model, okay, if we run this model here, okay, so well, basically its prediction is test loss 0.3, like a 0.3%, training loss 0.3%. They're reasonable because it is so easy to classify, right? So it's positive. Of course, weight is 2 points positive, right? Because negative side yellow, positive side blue, so it is positive. How about we remove this one and only use this one? Okay, let's try it. So again, well, because of some values over here, couple of them are not so good, so not as good as previous one, but still is a reasonable classification into the positive value, into the negative value. It is not so bad after all. Okay. Okay, let's stop the model. Here, epoch is the iteration basically. It iterated model. So 1455. So running rate is every time we iterate the process in each epoch, how much we learn. Okay. So it's the speed of learning. If speed of learning is too fast, it is not like a fine grained. If learning rate is slow, well, if we give enough time, we will learn a lot eventually, but it will take a lot of time. Okay. Activation. Well, we have a bunch of functions, ReLU function, tanh, sigmoid, linear, and here ReLU function is like ReLU function looks like this one. This is the ReLU function. And then we have tanh. Tanh and sigmoid is looks like this one. And the linear function is, of course, this one. Okay. So here in this case, I think, well, even if we use linear, it doesn't matter. Okay, it is fine. And then tanh, ReLU, everything should work similarly. They're fine. Okay. And here regularization is to make model more robust. Okay. So yeah, regularization rate to make model robust. Okay, so this problem is like a classification type. So we are testing plus and minus only. So it is like classification type. And then here we have ratio of training and test data set. So we have data. So well, here it is 50-50. Okay, 50-50, which means that we split the data half. So we use half of data to train the model and another half to test the model, basically. So like if we change this, now we use 70% of our data to train the model, and remaining 30%, we keep remaining 30% at a separate place. And then once we finish the training, then we put the model to the test using the test set, okay? So we can, of course, introduce some noise. If we introduce noise in the case, right? Well, with zero noise, it is so perfectly, with zero noise, it is so well, the data is very clean. But if we increase more noise, then, well, it is not so, right? Not so well distinguished. So if we include more and more noise, of course, then it is more difficult to predict, of course. Yeah. Batch size, how many samples we put for each epoch. Okay, so let's put batch size like 10. So we put 10 data per epoch. Okay, put 10 data together. Okay, so let me oh yeah, let me delete all the drawing. So apparently here, let's for illustration, let's make zero noise. So very clean. So it's distinguished, right? So next, what if we include x1 and x2 together? If we include x1 and x2 together, then our model is like y equal like alpha plus beta 1x1 plus beta 2x2 x2. Then we have some linear, we have a line over here, and with the line, maybe we can draw line like this one, right? If we use x1 only, we can draw line this way. If we use x2 only, we draw line this way only. But if we use x1 and x together, now we can spin the line, something like this one. Okay, so let's try it. Let's execute the model. Yes, exactly. So yeah, it is. So well, the test loss is zero, training loss is, so it is a perfect classification. Let me see the test data. Yes, test data again, yeah, perfect classification. Let's increase some noise this way. Let me see. Still, it is a reasonable classification. Okay, reasonable classification. Good. Now let's use different data set. This data set. Wow. Let me use zero noise. Okay, zero noise, and then let's do this one. So well, now it is a bit slightly more complicated data. So we have negative over here, negative here. We have positive, right? So now clearly, now we need a term like x1 multiplied by x2 term, right? x1 multiplied by x2. Then like plus, it is plus, minus, plus, minus, plus. So maybe it works. So let's try it. So again, with zero hidden layer, let's include this one and run. Well, it's reasonable, right? So it predicts well, and then let's see the test set. They are fine. Okay. Well, even if we don't use x1 and x2 and this one only, then clearly it doesn't work, right? Because we can x1 and x2, and then using x1 and x2 to explain the data. Because, however, in any direction, if we draw straight line, we cannot simply classify the data, okay? But even if we don't have x1 and x2 over here, even without this, maybe by including some hidden layers, we can make a non-linear function. So let's add 2 neurons over here, and then let's try, right? So, well, now we have some non-linearity, but it is not yet clear, not yet perfect, slightly better than before, but still we want more accurate classification. So let's add more layers. Then, well, now it is much better. Yeah, much better. So more hidden layers. It should be even better. Getting better and better, right? And then maybe we can increase the neuron over here. Now, yeah, neuron over here. Very complex model. Now, okay, now it is as good as before with X1 and X2. So it is now reasonable. But now we have one important lesson. Well, if you don't have insight, you can make model unnecessarily complicated. It is a complex model. You have two features and you have three hidden layers, and each layer you have three neurons. It is very deep learning model. And actually this one is not even necessary. You can leave this one. Okay. Now, okay, it is still as good. Which one? So it is again idle. Okay. This one, okay. Now here, this one is idle. So we can remove this one. And then, yeah, remove one and we can run again. Yes, okay. Ah, yeah. It is, okay. Regenerate, then stop and regenerate and start. Well, it is doing its best. Interesting. It is doing its best, but clearly, yeah. So one important lesson is if you don't have much insight. So, well, even if it is we are building artificial intelligence, still the mathematical insight or insight about data matters, because if you don't have insight, you will make your model unnecessarily complicated this way, right? But if you have good insight, you don't need this complicated model. You can simply reduce all hidden layers and reduce all features, and with just one simple features, X1 and X2, and you can build a very good model like this one. So insight is possibly, well, even if you are relying on artificial intelligence, still the insight is important. By this way, you can save time, you can save your computational resources. Okay, so next, let's try next data. Okay, this one. So for this one, okay, how we can do it? So it is clearly circle, right? Circle. So we have a circle. So at the center it is positive, outside it is negative. So intuitively, if we build a model, if that's one dimensional like X and Y, well, this kind of model should work, right? Of course, it is like a three-dimensional now. We have X1, X2. So we have like, yeah, ball structure. Yeah, I should explain this data better, right? So the smart way to build the model would be now include this square term, right? Square term, X1 square and X2 square. Okay, and let's do it. Well, it's good, right? Because from the data, we have intuition, so we can build a model, right? Again, if you don't have insight about data, maybe you will use X1, X2, and then run it. Clearly, it doesn't work. So maybe you are likely to make the model unnecessarily complicated, like this one. Well, this is complicated, have to work. Reduce. Okay, work. Okay. Well, this one is the last neuron. The last neuron is not much helpful, so we reduce one. Okay, so now, well, the second neuron, the first hidden layer, second neuron, again, not so helpful, so we reduce this one. Well, this one is not so helpful. This one is not so helpful. Yeah, yeah, this one is again not so helpful, so let's remove that too. And then run it. Yes, yes, something like that. So actually, we can remove this one as well. Okay, it is doing its best to run slightly more, slightly more. Again, if you don't have insight, your model is complicated, yet still not so accurate. Well, I think we needed this one. Okay, now it works. So unnecessarily complicated. But if we have a good insight about the data, by simply including these two, you can do this one. Okay. Next, now we have very complicated data. Now clearly, now we have some pattern, right? Over here, we have like pattern, but still we can find some insight over here, because if we split the data in this way, then we have a plus, minus, plus, minus, plus, something like that. If we split this way, then it's like a minus, plus, minus, plus. So we have some periodic, it is like some combined periodic function. So it is maybe good idea to include the periodic function, right? So in that case, we modify our features. So we put sign of the features over here. Sign function is like a periodic. Okay, so let's try sign function. Well, it is not enough. Okay, because now we have, well, sine and cosine, but we have like a diagonally also changing. So maybe we need more data. Okay, it doesn't work. So next, maybe we can, because it is also include some element of circle, so we can include this one. Now it is slightly getting better. Now it is time to include some hidden layer. So let's include one hidden layer, and then like a full 8 neuron. Okay, and then right, it's getting in better, getting better and better. Okay. And then how about we include even this one, every data, every features, every combination of features. Well, it's much better now. Okay. Now let's include now one more hidden layer, So it becomes like a deep learning model and add a neuron. Okay. So let's do it. Okay. We have improvement over here. I think it is enough. Right? We have a very small test loss and we have a very small training loss. How about adding more hidden layers? Okay. Oh, sorry. And then full neuron. Okay. Yeah, of course it works, but now we have many neurons are like idle. Many neurons are not so used over here. Okay. So let's use all hidden layers and then let's make most complicated model in this setting. And let's see, like extremely complicated model, and let's see the performance. And then, tanh, instead of tanh, let's do ReLU function. Then, so here's a regional prediction, right? But still, as you can see, we have a lot of idle, like we have a lot of idle neurons, like this neuron is completely like useless. They are the useless neurons. So there's room to improve this model, right? So, so let's remove this like 2 and then 2 over here, and then let's try. Okay, so the performance doesn't degenerate much. So, and then another interesting finding is that now you can see the role of each hidden layer. So it is like input. The very first neuron is like very simple shapes. But as we move to this one, now we have more and more complicated shape. right? This one. So as we move this way, the neuron accumulates more and more knowledge and they become more abstract. And let's the test data. Test data. So it matches test data also very well. Okay, good.